Hi everyone, we are Marwan and I are the current signal processing chapter's chair, and we are going to hear a presentation by Professor Dragotti. So Professor Dragotti is currently a professor of signal processing at the Electrical and Electronic Engineering Department of the Imperial College of London. His research interests include sampling theory, wavelet theory and its application, sparsity-driven signal processing, and computational imaging. And he is also an IEEE signal processing distinguished lecturer. The title of his ongoing talk is New Sparse Sampling Methods, Time-Based Sampling and Sampling Along Trajectories. So I let you the...
Okay. Thank you very much, Emma. Can you all hear me? I hope so.
We can hear you.
Ok. Merci beaucoup, Emma. Merci pour votre introduction. J'aurais aimé être à Bordeaux avec vous, mais c'est assez compliqué de voyager avec toutes les restrictions de Covid. Donc, je reste en Angleterre et je vais donner mon talk en anglais. Okay. So that's as far as I can go with the French, but I hope that's a little bit a way of saying, thank you for this kind invitation. And I'm sure next time we'll do that in person. Let me try and share my screen, and so that I can share my slides. Right. Sorry, give me 1 second. Okay. Oops. Sorry. Okay, I believe you can see my slides. Shout if you cannot. Okay. And so, as Emma anticipated, in this talk, I'm going to give you an overview of the work I've been doing over the last 15 years, probably in the area of sampling. Okay, in particular, what is known as sparse sampling. And in particular, and I'm going to focus on some of the recent activity in the area, and in particular, this idea of sampling based on timing informations and on sampling along, let's say, trajectories. I'm going to present joint work with several students of mine, but there's also work with some colleague of mine. This is Thierry Blou. He's a French applied mathematician. He's in Hong Kong now, works at Chinese University of Hong Kong. Martin Vetterli from EPFL, and Simon Schultz, who's a neuroscientist at Imperial College, and is someone I work a lot with. And the others are former or current students of mine. So the fundamental first point I want to make is that we've seen huge advances in new sensing and imaging techniques over the years, and so with really unprecedented capabilities, and that could give us the possibility to access the real world, the physical world, with unprecedented precision and resolution. At the same time, we are still not there, so there is a need to develop methodology to use this data in the most effective ways. But also, these new technologies bring new scientific questions, especially new questions on how we could and we should sample, or also how we should pose this sampling question, which is the questions of how we should get samples from the real world and then use them to retrieve as much information as possible, the physical real world. So let me make a few examples of these techniques and also the question that they can raise. So the first area where really we've seen a lot of progress is in the area of microscopy. And within microscopy, I'm particularly interested in fluorescence microscopy, which is used to monitor the activity of the brain. And so here is an example. Sorry, let me try and see whether I can show that to you. So this video here shows you the type of signals we can get. This is a brain, the tissue of the brain. And so that's the type of video that we can get. And the things that becomes brighter, okay, these sort of cells are actually neurons. And neurons encode information through generating pulses, which are known as action potentials. And really, for neuroscientists, the fundamental question is to understand when neurons are firing, when a larger population of neurons is firing, and work out how information is encoded through these mechanisms. The problem with this technology is that it is very good in terms of spatial resolution. However, if we then look at a single neuron, okay, and then look at the type of signal that we see over time, then we get a signal like this, which is really a stream of pulses, a stream of these action potentials. The difficulty is that the resolution in time of this type of devices is very low. This is because they are based on scanning approaches, scanning techniques, and so they tend to be slow. And therefore, we need to develop some method to enhance the resolution here, okay? And that is a sort of sampling question. Similarly, we have another type of microscopy, which is known as electron microscopy. And in particular, here I'm interested in something called cryo electron microscopy. And here the idea is that, for example, you want to work out the 3D shape of a virus, right? The coronavirus, for example. Okay, and so what happens is that you take a sample where there are various samples of your virus, okay? And then you freeze this sample. So imagine you have a volume which contains several of your viruses, and then you freeze that, okay? And then you take an image which is a single projection, okay? So that will give you a 2D image of this volume. And so what you're seeing here, right? So these are all projections of a 3D shape, all right? And since you were originally in the volume, these shapes are rotating in different positions. Therefore, each of these projections is from a different angle. And so if you knew the angle, right, then you could be able, by combining all these projections, to work out the 3D shape of this object, which is, again, for example, a virus. The difficulty is that you do not know this projection, right? Because all these samples were in this 3D volume which you have frozen. And so you're faced with the questions of reconstructing a signal from measurements which are taken at an unknown location, in this case, at an unknown projection. And so that's a completely different form of sampling problem, because normally, if you go back to this example here, you have some measurements and you know when you took them or where you took them. Whereas in this new context, you have no idea of where they've been taken. And so you're really trying to reconstruct the signal from measurements taken at unknown locations, which is actually a much harder problem. And then, another technology which is really, becoming more and more pervasive and important is the technology related to sensor networks. So you're now able to sense the environment, many phenomena in the environment, for example, the temperature fields, or maybe measure nuclear fallouts, etc. And you use essentially sensors distributed in space, and they give you measurements, and then you're trying to collect these measurements to infer the distributions of that field along the entire environment. Now, one typical way, for example, to measure, right, let's say physical fields is by using, for example, drones. They could fly in an area. So imagine here you have, for example, a fire, right? And then you're trying to measure temperature, to get temperature measurements, okay? And from there to work out, for example, where the fire is, okay? And maybe you would send a drone right there, because maybe you cannot get that closer, okay? So the issue then is that, first of all, the drone moves, let's say, along a trajectory. So you take a lot of measurements, but they are all concentrated along this trajectory. So you have something which is extremely non-uniform, right? A lot of samples in some concentrated region and not much samples in other regions, which poses the questions on whether you can reconstruct the entire field by only using these very concentrated measurements. The second issue is that sometimes you do not know the trajectory of the drones, right? Because you do not have absolute coordinates of the drones. You might be in an indoor environment or in a situation where GPS doesn't work, etc. And so here you're back to a problem similar to the one I mentioned before. So it's the problem that you get the measurements, but you do not know where they were coming from. You don't know where they were taken. And so you're faced with this extremely ill-conditioned problem of reconstructing, let's say, a physical field here from measurements taken at unknown locations. And that's a topic that we're going to cover. And then I want to briefly mention, also the idea that, for example, we try to design, to construct cameras which are faster and faster, so high-speed cameras, so that you can sort of image very fast, events. Now, the problem of high-speed cameras, and that's one example, but that's the general problem with traditional sampling, is that if you want to go faster, you just try to take more samples. So, for example, of a camera, you just try to increase the frame rate. So you try to develop a technology that is able to have, rather than the usual, I don't know, let's say 60 frames per second, that you can go to the order of hundreds, or even in some few cases, order of thousands of frames per second. The problem is that you take all these frames, most of them are essentially taking measurements of the same scene, so there is no new information, and so this approach is extremely energy inefficient. And so there is a need to find a new mechanism to sense, which would be not only fast, but also energy efficient. And we want to achieve that by taking inspirations from, for example, the brain, or in general from biology and the way the sensory system works, using the so-called integrate and fire paradigm. So based on this overview, what I'm going to do in this talk, I'm going to formalize a bit more what we mean by sampling, what is the sampling problem, and then highlight a little bit of history, if you want, and in particular talk about sparse sampling and compressive sensing theory, which was very popular about 10 years ago, but it's something that we are going to use in order to then develop new methods for energy efficient sampling, which would be bio-inspired. And in this context, I'm going to talk about sampling based on timing and the integrate and fire systems. And then I'll also look at the problem of sampling at unknown locations, and in particular, the problem of estimating, let's say, temperature fields using mobile sensors, so like a drone, which moves along trajectories which are unknown. And then we'll conclude and give an outlook. Right, okay, so if you think in terms of the standard sampling problem, in sampling you have your continuous time, let's say, functions that you observe with a device that could be the microscope or a normal camera. And we can simplify this and assume that this is just a linear system, okay? So that introduces inevitably some form of distortions. You can think of the lenses of a normal camera. They blur a little bit the scene. And then the distorted signal is sampled, typically at uniform intervals. That will give you the samples yn. Now, if you just do the maths, okay, and go through this process, then you realize that y is the convolution between x and the shape of this filter, the unit impulse response. And then this is sampled, so you take these samples at intervals which are multiple of t. And then what we do, we replace the unit impulse response with its time reverse version. Okay, we take something which is just time reversed, is the function phi, which is called the sampling kernel. And by doing that, we realize that the samples here really corresponds to the inner product between the function x and this sampling kernel, but shifted version of the sampling kernel, where the shift is a multiple of your sampling period t here. Okay, and so the fundamental question then in sampling is, given this set of measurements yn, are there cases in which I can claim that there is a one-to-one mapping with the original signal? So essentially, cases in which I can say that given these measurements, I can reconstruct x with no error. And then obviously the other question is, what are the acquisition devices I need to use in order to have this one-to-one mapping? Or in other words, what are the correct sampling kernels that I should use? And also, finally, what are the algorithms that I should develop in order to do this reconstruction? So in the traditional approach, the assumption, so the modeling assumption on the signal x to allow reconstruction is that the signal is, for example, band limited, okay? Now, a band limited function can be expressed as actually a linear combination of a single prototype function phi and its uniform shifts, okay? And in the case of band-limited function, phi would be the so-called sinc function, okay? And so if you use this expression, an arbitrary linear combination, but this phi is the sinc function, and then you take uniform shift of the sinc function, then this x will always be band-limited. But the interesting thing is that you can go beyond band-limited functions, and you can use this model here and replace phi with alternative functions, okay? And a typical setting is the one in which we assume that phi is the so-called polynomial function, and that will lead to functions x that looks like piecewise polynomial signals. And these signals are called shift invariant, signals that lies in shift invariant subspaces. Okay, so that's the traditional approach. Under this approach, it is possible to reconstruct X from the samples. You just need to make sure that the acquisition device is related to this prototype function phi here. And then the reconstruction process is linear. It's very simple. You take the samples that you obtain here and you filter them. And the shape of the filter here must be exactly equal to this shape. Okay, so going back to the standard band-limited case, phi is the sinc function. So this filter, its shape must be the sinc function, which means that this is actually a low-pass filter, right? Because the Fourier transform of the sinc is the low-pass filter. And so we go back to the traditional, let's say, Shannon sampling theorem that says, given a signal, maybe filter it with a low-pass filter, and then given the samples, filter it again with another ideal low-pass filter, and then you get reconstruction. And if the original function was band-limited, that would be perfect reconstruction. The problem of this framework is that the modeling that we're using is actually not general enough. Okay, if we think of band-limited functions, the reality is that there is not a single real-life signal which is band-limited. Okay, many signals are approximately band-limited. We can accept that, but not a single signal is band-limited. Okay, so that model is a little bit too restrictive, and we would like to find more general models that would encompass more signals, more real-life signals, and then develop methods for reconstruction. And so the idea that became very popular about 10 years ago was that we could actually think of signals as signals which are sparse in a proper domain or in a proper space. Okay, for sparse really means a signal that you can describe really with a small number of parameters. And so one approach to solve this is what is known as compressed sensing. Okay, and in the standard compressive sensing framework, what you do, you take your signal X and you discretize it. So you model as a very long vector. Okay, and then in its simplest incarnation, sparsity means that you assume that X has only a small number of non-zero entries. Okay, then since you have discretized the process, the filtering here is converted into a matrix, a fat matrix here. And then when you take this product, that will give you your samples. So each entry here would be one of these measurements, okay? So this matrix formulation here is equivalent to what I have here. It is just that we have discretized everything, okay? And then in compressive sensing, this problem is obviously normally ill-posed because this vector is much smaller than this guy here. So normally you cannot reconstruct X from Y, but we know that in compressive sensing, one tries to solve this problem posing a proper convex optimization, problem. And then using this sparsity as prior, okay, it is possible. So Dono and Candace demonstrated some strong recovery guarantees, and that created a lot of excitement because essentially that demonstrated that there are many cases in which, given Y, you can reconstruct X exactly. Now, in our framework, we are going to look at sparsity from a slightly different point of view. And that's because our idea is that we don't want to discretize the process. Because if you're doing something, discretizing the signal is a self-defeating type of approach. And so we want to stick with functions which are continuous in time or space and try to model them as sparse, but with a sparsity which applies to continuous time functions. And so our type of model is based on what is known as signals with finite rate of innovation. And so the idea is to say that all the signals we are going to consider are signals which are completely specified by a small number of parameters. And the simplest instance of a signal with finite rate of innovation has this shape here, okay, and can be seen as, for example, a stream of pulses. All right, so this is a typical example of a signal with finite rate of innovation. So here the idea is that you know the shape of the pulse, which is phi here. What we do not know is the location of the pulse, tk, which can be anything on the real axis, and the amplitude of the pulse, okay? And so under this model, the idea is to say, okay, I then take samples of X, and my hope is that from the samples, I can retrieve the three parameters, so the xk and the tk, or in other words, the locations and the amplitude of these, let's say, pulses, or here, locations and amplitude of these pulses, because then if I can retrieve these parameters, I can obviously reconstruct the signal exactly. While the stream of pulses is the most intuitive example of signals with finite rate of innovation, there are many other signals that fall within this model. For example, piecewise polynomial signals, piecewise constant signal like this one here is another example. Okay, so these are the classes of signals we are going to focus on. And then the question is, okay, now I'm given the samples, yn. Can I reconstruct these signals? Okay, so let's assume that our signal is a stream of pulses to make our life simpler. And so remember, we're trying to retrieve the locations and the amplitude of these pulses. Okay, now the problem here is linear in the amplitudes, because if I know the location of the pulses, okay, so if I fix that, if I take a linear combination of two stream of pulses, I get a new signal, which is again a stream, for example, of k pulses. But the problem is non-linear in the location of the pulses. So we need to develop a method which is non-linear. And our idea is the following. So given the samples yn, we want to modify them in a way that we get a new set of measurements that I call Sm. And we want this measurement to have this shape here, okay? Where the UKs, which are known as exponentials, because these are to the power m, okay, which is a whole number, an integer, okay? The UK should encapsulate the information about the location of the pulse, okay? Whereas the BKs encapsulate the information of the amplitude of the pulses, okay? Now, the reason why we want to try and convert the samples into this new set of measurements is because if I am given these measurements here, okay, then I can apply a method known as Prony's method, which is actually able to automatically extract the UKs and the BKs from this sum here, okay? So the sort of pipeline is clear. I observe the samples yn. I need to find a specific manipulation that gives me the Sm, and the Sm must have this shape here. And if that's the case, then I feed the Sm to Prony's method, and then Prony's method extracts the BKs and the UKs, and from there we retrieve locations and amplitude of the pulses. This method is known as Prony's method because it's due to Baron de Prony, a French mathematician that discovered it in the late 18th centuries. Right, so let me try and show you how we can go from this yn to Sm with this shape here. And we can achieve that if we can pick the sampling kernel phi, or if the sampling kernel phi behaves in a nice way. So remember, phi is the shape of the, let's say, behavior of your device. So that's a typical shape, for example, that you could see. Okay, and so the idea is that what we want to do, we take this sampling kernel, we take uniform shifts, and we take weighted sum of this uniform shift with coefficient Cmn, and we want to find this set of coefficients such that this sum is equal to a complex exponential. Okay, so let me try and show that visually. So the idea is that this is, for example, one version of the sampling kernel. Then I take a shifted version by an integer here, which is shown here. Then I take another shifted version, and so on and so forth. And then I combine them, linearly combine them using weights that I am going to decide. And I want to pick these weights so that when I sum all these black guys, I get a curve, which is a little bit like the purple curve shown here, which is actually a complex exponential. So, okay, that's the real part of the complex exponential, which is a cosine wave, okay? And the idea then is that if I change these coefficients, then I'm still able to reproduce an exponential, but maybe with a different frequency. And so maybe it oscillates more slowly. So how am I going to find these coefficients? Okay, and that's actually a sort of standard problem in maths to some extent. So you have a set of functions, phi is a single function, but then all these uniform shifts. And you'd like to take a linear combination so that this reproduces approximately a new function. Let me call it fmt, okay? And so what you would do normally when you try to achieve this approximation, you look at this space, which is covered by your function phi and all its uniform shifts. So you look at this subspace, and then what you do, you try to compute the projection of this function f onto this space, okay? So you try to compute the orthogonal projection. And to compute that, you just need to use the so-called orthogonality principle that says that the error in your approximation, which is shown here, must be orthogonal to the space onto which you are projecting, okay? Which is like saying that this error in your approximation must be orthogonal to the function phi t and its uniform shifts, okay? So this condition here, okay, gives you enough equations essentially to find your coefficients, okay? And these coefficients will guarantee that you are finding here the best possible approximation in the least square sense, because this is what the projection does. Now, in our specific case, remember the f we are interested in is a complex exponential. And also we have this peculiar situation in which here we have only a single prototype function phi, and we are looking at the uniform shifts. Now, because of all these constraints, it turns out that one can find a closed form expression that would satisfy this condition here for the coefficient Cmn, and the coefficients are given by this expression here. And the fundamental thing to observe is that what we are saying is that they depend on the Fourier transform of the sampling kernel evaluated at the frequency that you're trying to reproduce, okay? And so good kernels for us are sampling kernels which have a Fourier response, Fourier transform, which is relatively flat around the frequencies that we are interested in, okay? But that gives us a closed form expression to find the coefficients here. And given this, we know that that means that this guy here is very close to these exponentials. Now, by doing that, then we can achieve what we wanted to achieve at the beginning, right? Which was to say, given the samples y, we want to convert them in this new set of measurements, which should be good for Prony's method. Okay, and in fact, what we do is the following. Given the measurements, we take weighted sum of these measurements as shown here, where the weights are these coefficients that reproduce exponentials, okay? And then this weighted sum will give us a new measurement, which we call Sm. And now I replace y with its definition, which was the inner products. Linearity of inner product means that this guy can go inside this integral here. And now this quantity here is exactly the quantity that reproduces approximately exponential, because this is the way we had designed these coefficients here. And so this guy here, we can assume is an exponential, okay? So if we assume this is an exponential, then this inner product is this quantity here, okay? And now let's assume that x is a stream of pulses, which was our original assumption, a stream of Diracs to be more precise. Then I plug this expression into this integral here, and I end up with this sum. And then if I pick several frequencies here, and I make sure that they are all evenly spaced, then this sum here is exactly that sum, which is good for Prony's method. Okay, so let me sort of summarize the basic framework in sparse sampling. So you sample your signals and you get the measurements yn, okay? Then you combine them using the weights Cmn. Now these weights, we had designed them beforehand by knowing the shape of phi, the sampling kernel, and they are designed in a way that we make sure that they reproduce these exponentials. But this weighted sum gives us these new measurements, and then through manipulations, we have discovered that these new measurements correspond to this sum here of a power sum, which is good for Prony's method. So we feed this to Prony's, and then Prony's method will produce the U case and the B case. From the U case, I retrieve the location of the pulses, and from the B case, I retrieve the amplitudes. So that's the basic framework of sparse sampling. Can be generalized to work with more complicated signals, but that's always the same type of idea. So let's see this in action and see what happens, on many applications. First, let's focus on an idealized setting. So here I have a stream of 4 pulses, okay, and each pulse has a shape which we know a priori, and is a shape of fast rise and then slow decay, okay? Then we take the samples. These are the black guys here. These black dots are the samples of this guy here. So it's filtered and then sampled. And then from the samples, we do essentially the trick that I mentioned before. So weighted sum with proper weights. This gives us something that we can feed to Prony's method, and then Prony's produces locations and amplitude of these pulses. And then given that, we can resynthesize the signal and the signal is exactly equal to the original signal. Okay, so we are perfect reconstruction in this context. But the interesting thing is that this basic idea can be used in many practical applications. So let me go back to the neuroscience example I mentioned at the beginning. So remember, this signal here is a stream of pulses. It's generally a stream of pulses. Each pulse is an action potential, is related to when a neuron is active. Okay? Remember, this guy is a very low resolution in time. In this specific case, we sample at 7 Hertz, so extremely low. Okay? And we would like to find when the neuron fired, so which is really like finding the location of each of these pulses at very high resolution, okay, despite all this noise. So we run essentially the method I mentioned before, and this is what we retrieve, okay? So in red are the detected spikes, and in blue are the original spikes. Now, this is real data, but we acquire the data in a way that we have access to ground truth information at very high resolution, okay? There is a way to do the acquisition so that we know with high precision when the neuron was firing. And so we can check whether we are doing well or not. And so you can see that we are very good. We can retrieve pulses with very high accuracy, but also we make errors. For example, we missed this pulse completely. When we compare this approach with the other existing approach, we actually do much better than any other state-of-the-art method. But also is a fast algorithm, this sparse sampling method, so can be run in real time and give us a virtual increase of resolution, which in this case is by an average factor of 3. So in other words, through this sampling-based reconstruction, we can reconstruct a signal which is the same that we would have seen had we acquired at 21 Hertz rather than 7 Hertz. The same type of ideas can be used for imaging. Okay, and again here, just showing you an example. So this is a real image. So this is a picture of the Victoria and Albert Museums in London, and this is a specific artifacts. Okay, a very small feature of the building. And so even though the camera is a good one, when you look at these features, okay, you can see that we are losing resolution. All right, and then we can run this sort of sampling methods. So the samples here are the pixels, and then we run this method. We retrieve, in some sense, at high resolution, the essential information of the signal, and we can reconstruct this image, which is much better, and it is at higher resolution. So we increase the resolution by factor 4 here per direction. Okay. And then I want to show the last example, which is in the area of sensor networks. Okay. So here we are measuring the temperature of a certain region, okay? So this is the region here, and these dots here are where the sensors are. So here is where we measure the information. And if you wait enough and you look at these pixels, you'll see that at a certain point, that's the time they will change color, okay? That's because there has been an event, so a heat source has heated this plate which we are measuring. And then from these measurements that you're seeing here, we would like to reconstruct the entire field, okay? Let me clarify that this is real data, but is obtained in a very controlled environment. So what we did is we took a silicon plate, okay? And then we use a heat gun to create a point like heat source, instantaneous. And then all the heat propagates. And then from the measurement we take, use a thermal camera to see how the entire field is evolving. Then out of the thermal camera, we just took a few pixels, and these would represent our sensors, okay? The measurements that we can see on each of these sensors over time are like this, okay? So this line is when the event happened, all right? And then you can see how noisy the data is. Now, based on this data, we try to reconstruct the signal, okay, so from these pixels. And so this is the type of signal we reconstructed from only this information here. And so you can see the event happening. So here is this heat gun, which, hit a very concentrated region, and then the heat distributes, gradually on the whole plate. But what is interesting is that, remember, we also have the ground truth data, okay? And so we can compare what we reconstruct with what is the ground truth. I think it's quite nice to see that the reconstruction is extremely accurate, which is quite notable, in particular, given the small number of measurements that we had. Right, so this is where we are so far. So this is all good. I think that shows that sparse sampling is a framework which works in practice, can have an applications on a rich variety of different contexts. So what we want to do is to build on that to now address, let's say, more current problems. And so I want to focus on two instances of, let's say, more modern problem, as I mentioned before. So one is about developing an energy efficient way to sense information. And the other is about reconstructing when samples are taken at unknown locations. So let me focus first on this case here. And let me highlight with a simple example why things, the way we do currently, are inefficient. Okay, so let's assume that your problem, okay, is like a primary school, problem, right? You want to find a way to measure rainfall over, for example, the summer period. Okay, so you've been tasked with that, and the simplest thing you could do, right, is to take a bucket and put it maybe in your back garden. Okay, and then what you can do, you can measure the amount of rain that falls in the bucket at regular intervals. So maybe you start 1st of July, and then you check on 10th of July, and maybe this is the amount of rain that fell in the bucket. So what you do, you write down how much rain had fallen up to the 10th of July. You empty your bucket, and then you repeat the process. So you keep the bucket for 10 days, and then after 10 days you measure. And maybe this is a bad summer, so July is very rainy, so you have a lot of rain on the 20th of July. So you write down how much rain you have measured, you empty your bucket, and then you repeat the process other 10 days. And maybe you still have a lot of rain, so 30th of July, you still write down how much rain you found, and then you empty your bucket. However, remember that the summer in countries, not in the UK, but in countries like France or maybe south of Italy, where I'm originally from, the summer is normally sunny and dry, okay? So that means that normally you're not going to see rain maybe for a month or 2 months, right? And so maybe here in this example, after this period of rain, then there is no rain anymore for a month, okay? And yet what happens is that you still have to check your bucket every 10 days. So on the 9th of August, you go and check, the bucket is empty. You write down bucket empty. Maybe if there is one drop, you remove it, and then you repeat the process, and then is again empty of the 19th of August, and maybe you have to wait end of August to start seeing a little bit of rain again, okay? So that's the way we do sampling, right? So we measure regularly, okay, a certain, information. And if there are no events, so if nothing happens, we keep getting measurements, okay, even if they are all zero, like here, okay, there is no rain for a month, but we still have to check the bucket regularly. And if you want to increase the precision, you need to take more samples, which means you are even more inefficient during these months. So the idea is that we should change the way we sense information and just sense it when there is an event happening. So in this context here, what we could do is use a completely different technique. We should put the bucket in our back garden as before, but then we leave it there, and we take an action only when the bucket is full. So we wait, and then when the bucket is full, what we do, we write down the date in which that happens, so the time if you want, so 18th of July in this example, and then we empty the bucket, put it back, and leave it there, and just take an action when the bucket is full again. So maybe remember, in this example, July was a rainy month. So maybe after 10 days, the bucket is again full. So what we do, we write down the date. That was 28th of July. We empty the bucket and leave it there. But now remember that August was extremely dry. So with this new approach, for the entire month of August, we don't have to do anything, okay? And the next time the bucket is full maybe happens in September, okay? It takes a while for the bucket to be again full. So you just write down 2nd of September, the bucket was full, and then you empty the bucket, okay? And then you can see that here you're saving a lot of energy, because if there is no event, then you don't do anything. Now, this second approach is the approach which is used by nature, and that's the interesting thing, right? Because in sensory systems, okay, what we do, we have the equivalent of what we call integrate and fire, which is like the bucket. The bucket integrates, and then fire is when the bucket is full. And then when the bucket is full, you fire an action potential, right? Which is like for us writing down the date. and then we reset. So we empty the bucket and we repeat the process. And this is the way neurons work. So when you have some sensory information, then you collect it, you integrate it, and at a certain point, if you have enough of that, then the neuron will fire, or several neurons will fire, and that will trigger all the actions in our brains. So what we like to do is to develop a completely new way of sensing, which is inspired by nature, and that we hope will be much more efficient. Now, there are devices which are emerging, which are based on this idea, and they are sometimes called neuromorphic sensing devices because they try to mimic the nature. Okay, and so one example is a video camera, and here I have the video that I'm going to show you. So the camera, each pixel behaves a little bit like a neuron. So what the pixel does is, if there is no change in the scene, the pixel doesn't do anything. And then if you have a change, then the pixel sort of integrate the change, and if it is, an important change, then it will fire. Okay, fire means that neuron will be active, and so what you store is which pixel was active and at which time. And since you can store the timing information on very high precision, you can, sort of encapsulate informations related to things that change very quickly. And so you can have implicitly a very fast video sequence. And so here is an example of the video with these new cameras of a flipping coins. Oops, sorry. So you can see here the coins which is flipping. This is clearly slow motion, right? But this is real data, okay? We're flipping coins, and you can see that only the pixels around the coins which are seeing big changes are those who are firing, okay? Otherwise, there is no firing. So what is interesting here is that we are getting very fast sensing, if you want, but it's also very energy efficient, okay? Right, okay, so for us, there are a couple of fundamental questions we want to understand. The first question is, okay, can I encapsulate the information of a normal signal, a video sequence, a complicated signal, into this timing information in a way that then I can reconstruct the original signals, okay? There will be a question like saying, can I reconstruct the original intensity video from the data that I've just shown you here, okay? And the second question, which is related, is, okay, are these current cameras the best cameras? Maybe there are better ways to design cameras based on the same principles, but in a way that they could, store much more important information about the signal. And so trying to understand something based on timing would give us these two very important answers. First of all, it could provide guidelines on how to design these devices, but also guidelines on how to reconstruct, for example, the intensity video from the data. So mathematically, the, let's say, integrated fire system is modeled as shown here. So you have your incoming function, you integrate the function, okay? And then once the integral reaches a threshold, also known as trigger mark, you fire, okay? And then you store the timing of when you fired, okay? And after you fire, you reset your integrator. So it's like emptying your bucket. Now, this is the normal type of system which is used, and one can show that from this timing information, you can immediately retrieve some information about the amplitude of X, and then the question is, from there, can I reconstruct X exactly? To understand that, let's look at the simpler example of time encoding machine, which is the comparator system. Is not a great system from a practical point of view, but it is easier to understand, right? And here the idea is that you have your signal, and then you compare it with a known function, maybe a sine wave. So you just take the difference, and then you store the time at which this difference is equal to 0. Okay, so here is an example. This is your function, your reference function, so gt, and this is your signal x. And then when the two functions are equal, you are firing, okay? Now, clearly, from these timing informations here, since you know g, you can work out the amplitude of x, because at distance tn, we know that x must be equal to g, and therefore you retrieve the xtn. So you have some information about the amplitude here. The same would apply for this guy here. It's a little bit more involved, but it's similar type of result. So the question is, given now this new set of amplitude measurements, can I reconstruct x? And the interesting thing is that we have some positive answers. So they were produced by Aldruby and Grogenig in the past. Let me give you an intuition on how you can get this answer. So the idea is the following. Let's go back to our example. So we know that we emptied our bucket on the 18th of July. And then we know that the bucket was full again on the 28th. So what we know for sure here is that since by emptying here, the bucket here, I've sort of reset the information, we know that from the 18th to the 28th, there must be enough amount of rain for the bucket to be full, okay? There was just enough amount of rain to make this bucket full. Okay, so what I can assume is that it rained uniformly, the same amount of rain throughout these 10 days. So that's the most simplest and reasonable assumption. So that allowed me to work out how much rain there was from the 18th to the 28th. Then I emptied the bucket on the 28th, and I know that it was full again on the 2nd of September. So again, I can assume that it rained uniformly during this longer interval, and then I can find the amount of rain that dropped uniformly, because this must be exactly enough to fill my bucket, and so on and so forth. So I get a first rough approximation of my signal, and then I can use some prior. Maybe I can have a prior that says that, look, rainfall is a band-limited function. So you expect rainfall to be a smooth function, for example. So given this, I can project onto the space of band-limited function, and that is what I would obtain, okay? And then what I can do is that given this new estimate, I can check whether this is consistent with what I measured. So whether these would have led to the same timing for which the buckets were full. If the answer is yes, I'm done. If the answer is no, I repeat the process to correct for the error. So here is a more synthetic example. So you start with your function, you have the equivalent of these non-uniform samples. You do the piecewise constant approximation I mentioned before. You project onto the correct subspace that will give you the red curve. And then you resynthesize the measurement that you expect. You check the error. There is an error. So you do a piecewise constant approximation of the error. You project that in the correct subspace. And then you sum your first estimate with the new estimate. And this is what you obtain. And then you repeat the process. And then if you have enough measurements, one can prove that this iteration converges. So that's the strong results of Aldrup and Grokkening, okay, proving that you can actually reconstruct exactly the signal. The problem of their approach is that, first of all, it works for signals like band-limited signals. And we really want to go beyond that. We already discussed this issue. We want to be able to operate on sparse signals, okay, which are not band-limited, because they are more general. They can have impact in many applications. So that's problem number one. Problem number two, which is even more serious, is that the results of Aldrup and Grokkening applies if you have enough measurements, okay? And you actually need a number of measurements which is bigger than the number of measurements that you would normally have using uniform standard sampling. So that means that actually this approach is less energy efficient than existing approaches, and this is really not good for us. So we really need to come up with a completely different way to reconstruct the signal, and maybe use also other signal models to really have something which is energy efficient. And so here we want to leverage all the stuff that we learned from sparse sampling. And in particular, we want to play with the proper sampling kernel as we were doing in sparse sampling, and consider an alternative way to reconstruct, for example, use Prony's method for reconstruction. So here we propose an alternative sensing system. Rather than just having an integrate and fire system, as here, we have a filtering operation before that, okay? A little bit like we do in sparse sampling, okay? And we take a filter which, for example, reproduces exponential like in the previous case, okay? So we have sparse signals as input. They are filtered first, and then they go through an integrate and fire system. And then from the measurements, from the time information here, we want to reconstruct the signals. First of all, under this framework, okay, from this timing information, I can retrieve some information about X, okay, are again inner products, okay, as we had before, where phi is related to this sampling kernel. And the other difference is that this is non-uniform shifts, whereas before we had uniform shifts, okay? And then, so we have this, and then the question is, can we reconstruct, okay? So given this, given these samples here, these measurements here, can I reconstruct X? And so now the two issues we need to address is what are the right sampling kernel we can use to have reconstruction, but also what is the right density of samples that we need to have reconstruction. And here, remember that the signals are sparse. So these are signals which are determined by a finite number of parameters. So what we want to do is to make sure that each time there is a change in our signal, we get enough samples. So we trigger, fire enough so that we can retrieve these new parameters. But then if there is no change, like here, right, we don't want to have samples. A little bit like what happens in nature, okay? So we need to set the trigger mark in a way that is low enough so that we get enough samples here to retrieve this information, okay? Now, without going into details, the first good thing is that if we assume that phi has the same ability to reproduce exponential as in the original settings, then even if the shifts are non-uniform, we still preserve that ability to reproduce exponentials, but it's now local, okay? We can only do that in small intervals. So what we need to make sure is that in the small interval where we produce exponentials, there are all the innovations, all the events that we need to reconstruct, okay? And so this can be achieved if I pick a sufficiently small trigger marks. So based on the settings, so given a fixed signal and given a fixed phi, given a specific, class of signals and a fixed phi, we can find a trigger mark C, which given an event like a pulse, would trigger enough events, would trigger enough spikes so that I can retrieve this pulse here. And what we need is minimum number of spikes. The minimum number is actually 3, because we need the first one to sort of reset the system, and then the following 2 to retrieve the 2 degrees of freedom of a pulse, which is the location and the amplitude, okay? So based on the setting, one can come up with a precise answer on how to pick the trigger mark. And let me show that visually, right? So here you have 3 pulses, okay? And the blue is the filtered signal, and then that goes through the integrate and fire. And so after each event, we fire at least 3 times, okay? So here we fire 5 times, here we fire 3 times, here we fire 4 times. And based on this, from here, we can retrieve location and amplitude of this pulse, and then from here, retrieve location and amplitude of this pulse, and then for the last pulse. What is interesting is that after having triggered this set of pulses, nothing happens after that, okay, until we get a new event. So that leads to something which is more efficient. And that's a basic case, but we can derive similar results for more general signals. If you have something like a piecewise constant signal, then you have some events where, some action potential, yes, some action potential when you have an hedge, right? But otherwise, as you can see here, nothing is happening. So we become much more efficient. This can be extended also to video sequences. Now for idealized videos, we can get perfect reconstruction. Now what is interesting is that in our context, we need that each pixel behaves like an integrate and fire system, but with slightly different properties. So actually we can reconstruct if pixels behave a little bit differently, so bring some diversity. Let me show that visually here, okay? So on the left here, I'll show you the actual video sequence that we can reconstruct with no error. And on this other side here, I'll show you the type of video which would be generated by this new event camera, okay? So you can see the object has a specific shape, is a complex shape if you want, and then it moves, okay, in a certain way, okay? Oops, sorry. Let me show the video again, okay? So you can see the object. On the other side, you can see the various pixels which are firing, okay, and they are firing at different time, and there is also a little bit of a delay in order to be able to encapsulate enough information, okay? And but from this data here, we can reconstruct that shape and also the speed at which it moves with no error. Okay, good. So that gives you an idea of this area of research based on timing information. And I like to stress that this is really an emerging area of research. So it is really about, on the one hand, sensing using integrated fire systems so that you end up with spiking signals. But then there is also a fundamental question. So now you're going to process spiking signals, okay? And so, for example, there are new neural network methods which are device to handle spiking signals, leading to what is known as spiking neural networks. Okay. And the other thing is that, for example, people are using machine learning here to, for example, reconstruct intensity videos. Okay. So you train a network using this data here, and you teach the network to become used to reconstruct an intensity video. So it's a very active research area. There are very fundamental questions based on sampling, which I have highlighted here. There are other fundamental questions based on how you do learning with spiking signals. And there are also more practical questions. How are you going to learn things with standard network, but with this type of data? And I encourage you to look into this area, which is very interesting. Okay, I want to spend the remaining 5-6 minutes. Sorry, I'm probably running a little bit late. Talking about the last topic, okay, which is the one about sampling at unknown locations. Okay, and so let me remind you where we were. So the idea here is that you would like to, for example, estimate the temperature distribution in a certain region. And maybe you are measuring the temperature using a mobile device, for example, a drone. Okay, and so there are two issues here. First of all, the drone takes measurements along a trajectory, so they are really non-uniform measurements. The second question is that you do not know the trajectory. Okay, so what you're trying to do is to simultaneously estimate the trajectory and the temperature field. So this problem is linked to a very traditional problem in computer vision and robotics, which is known as SLAM. SLAM stands for simultaneous location and mapping. Okay, there were very relevant results probably produced 20 years ago of a robot moving in a certain environment, and then at a certain point the robot goes back to the starting point, is able to realize by looking at images that it is back at the starting point, and then based on that the robot could map the trajectory that it had completed and create also a map of the environment. Okay, so it was able to simultaneously locate and create a map. And so here we're trying to solve the same problem in a much more, if you want, fundamental ways, if you want. And here the idea is that we want to do mapping and localization when we measure a physical fields, which could be the temperature field, but could be also other fields, for example, acoustic. And in fact, there is an area of research which is known as acoustic SLAM, which is trying to do exactly that. So retrieve the acoustic, for example, of a room, right? And simultaneously work out the way you have moved. Okay, but again, from a fundamental point of view, all this is related to a much more fundamental question. The question is, I get some measurements, okay, and I want to reconstruct, for example, a signal, but the measurements are taken at unknown locations. Now, this problem was already observed by a guy called Browning, about 15 years ago. He looked at band-limited functions, etc. So it's not a new problem to some extent, but it is a very hard problem. Very often it's combinatorial. You need to try everything in order to find a solution to your problem. Normally, the solution is not unique, okay, if you do not have constraints, and yet it's a very relevant problem to contemporary applications, to modern applications. So SLAM is an example, but also the cryo-electron microscopy that I mentioned at the beginning is another example. Over there, you have unknown projections, okay? And it is very relevant, right? If you need to work out properties of a virus, right? You want this microscope to work well. The fundamental point I want to make is that in the case of diffusion SLAM, which is the one we are looking at here, the problem is sufficiently constrained so that surprisingly, we can find a solution to this problem, and that we can find it algebraically, so using matrices in some sense, okay? The solution is unique up to a rigid rotation, right? So we can also state something very strong about that. So let's glance at the solution. And so first of all, we need to understand the properties of the fields we are trying to measure. And remember, this is a temperature field. Our assumption is that the field is generated by localized sources. Now, if you have a very localized source that is generating a temperature field, the temperature field really will look like if you are in 2D, which is the case we are going to consider here, the field will look like a 2D Gaussian. And then what happens is that the variance of this Gaussian will increase over time, Okay, so when you go over time, this pulse becomes broader and broader, and the amplitude decreases. Okay, it's a little bit similar to the video of the temperature field I showed you before. Okay, so now in our case, we have a few localized sources, and then remember, we are measuring the temperature along a trajectory which we assume to be piecewise linear. Okay, so the first observation is that if I look at the measurements along the lines, the measurements will look like this guy here. So it's a stream of pulses. So that's again a signal with finite rate of innovation. And so from one of these signals, I can retrieve the locations and amplitude of these pulses. And now the idea is that from that, I hope to be able to reconstruct the signals. So the good news here is that this problem is ill-conditioned but is sparse. It is sparse because there is a finite number of sources, maybe k sources, and it is sparse because the trajectory is piecewise linear. So I just need to know, for example, the vertices to retrieve it. Okay. And the other important thing is that, as I said, the projections is a piecewise is a stream of pulses. So from each projection, I can retrieve the location of the pulses. Okay, which I'm going to denote. So, for example, the location of the first pulse along the first trajectory will be called y11. Second pulse along the first line here will be called y21, and so on and so forth. Now, through these guys, having all these priors, I hope to be able to retrieve the locations of the sources and the trajectory itself. Okay, so let me give you a geometrical idea on how we can solve that in high level. Okay, so let's focus on this line here. Okay, I can take the unit vector here, which is related to the direction of this line. Okay, which is this red guy shown here. Okay, you can see it here, and this is really given by this quantity here. This is a unit vector along the direction of your line. Okay, and then I look at this other vector here, which is the difference between the this point here and the location of the source k. Now, if I take the inner product between this vector here and this other vector here, which is shown here, this corresponds exactly to ykj, which is what I have retrieved. Remember, ykj is the location of this pulse here along the trajectory j. Okay, and this is what I know because this is what we have retrieved. Okay, ykj is this guy here or this guy here. Okay, so geometrically, I realize that ykj, okay, can be written in this way. So this is known, and so I can create a matrix omega kj, which is the difference between two of these ykj related to two consecutive sources. So this difference is this guy here. So I create a matrix omega where the entry kj is this one here, so related to source k and line j. And so geometrically, I realize that this matrix omega has this shape here, and so can be factorized into two terms. One is only related to the sources, and the other is only related to the directions of each line in the trajectory. Okay. The other thing is that by construction, this matrix has size k minus 1 times 2. This has size 2 times L, where L is the number of lines. So that means that this matrix here is of rank 2, necessarily. So what I can do, I can factorize this matrix using SVD. And so that will give me two matrices, which I'm going to call S and C. The matrix C will give me all the informations about the trajectory, and the matrix S will give me all the informations about the sources. And in this way, I can retrieve both. Okay. Here is a synthetic example. So that's the trajectory. Okay. Here are the sources. This is the data you measure, right? So this is along the first line here. Then you turn. This is the second line. Then you turn is the third line. Okay. And actually, there is noise in this data. So this is the noise. Okay. Now, what we do is we work out the location of all these pulses. And then based on that, we create that matrix. Then we factorize it, and then we retrieve locations and amplitude of the racks, the sources. Okay. Here we add some absolute information in order to make sure that this solution is unique. Otherwise, that would be up to a rotation. Okay, so I could get a rotated solutions of the ground truth signal, but that's still good. And here is on real data. It goes back to the temperature field I showed you at the beginning, right? So here I'm doing like in SLAM. So my drone is following a trajectory and then it's going back to the origin. So this is the data that we measure. This is ground truth real data, right, for each of the lines. And then we can estimate the trajectory. That's the blue line here, and the red one is the ground truth trajectory. And then we estimate the source location with the circle, which is very close to the ground truth source location. And so the problem can be solved with good accuracy. Okay, I think I can conclude now. Okay, and a couple of messages I want to convey to conclude. First of all, okay, something is in great shape. Okay, there are always something questions as soon as you deal with, interesting sensing devices. And in fact, the more sophisticated and flexible these devices become, the more sensing and sampling theory becomes important, okay? Because you have more degrees of freedom to play with the way you want to acquire informations, and that would lead to better reconstruction. So that requires understanding of all the sensing process. In sampling, this idea of sparsity remains really fundamental. So this idea that, okay, we need to model the signals so that we can understand what are the essential features in your signal, and then you devise method to sense and reconstruct these features in the best possible way. And then in many real-life problems, you always need better resolutions, okay? Resolution seems to be never good enough. We have these fantastic microscopes, but then resolution time is not good enough, okay? So you always need to improve that. We often sample nowadays at locations which are unknown, and that poses very new, interesting questions. And maybe we sample along trajectories, especially when you think of autonomous vehicles. And finally, sampling based on timing is relatively unexplored, I would say, but I think it's very essential area for fast and energy efficient, I would say, information processing in general. So that's an area where we really will end up working a lot, I think, from now on. I think I can conclude here. Thank you very much for your attention. I'm going to stop sharing the screen in case maybe there are questions or.
Presentation. We will ask you one or two rapid questions because we have another speaker scheduled. So we have first a question from a PhD student that can maybe come.
Maybe I will come to. Thank you, Professor, for this great presentation. I have a question. Is this process are suitable for satellite measurements, or the problem is the measurements is very far from the target? I think about altimeter application and something like this.
Okay. Okay. Right. So first of all, let me make sure I fully understand the question because there was some echo, right? So you want to know whether, for example, this time-based sampling can be used for satellite measurements, I think. Okay. Well, I don't have enough experience, right, to give you a good answer on that. The way, I'm not sure satellite is probably the best applications, okay? Because things over there, I guess, tends to be not that fast moving, maybe, okay? I would say in general, it is very useful to use this event-based technique each time you have situations where the signal you're measuring is extremely asynchronous, in the sense that maybe nothing happens for a while and then you have something which is relatively fast happening. Because then if you have a method which becomes active in some sense when the event's happening, then you can save energy and yet have very low latency, which is what you need. I'm not sure this would really apply in the case of satellite images.
But in low Earth orbit, there is still a problem. I'd like.
Emma, can you repeat the question? Or
Problem is the measurement. Sorry, maybe you don't hear me.
On a l'autre speaker, JC.
Yeah. Is it just a problem if the low Earth orbit but it's still a problem.
Yeah, you get cut from time to time, I guess. Maybe if you're sitting where Emma is.
He is asking if it's a problem when it's low Earth orbit. Is that right?
Yeah, is that correct? Yeah. You can't hear me?
Say it again. Is that the problem when?
When if the satellites is not the geostationary satellites, but low Earth orbit satellites.
All right. Okay. I don't have enough experience on that. Okay, to give you a good answer. To be honest.
Yeah, thank you very much.
I think yes. I just to stress one thing. So I mean, the imaging in satellite devices is extremely advanced. Okay, the imaging systems. Whereas these, let's say, event cameras still operate at low resolution, for example. So, if you were to place one of these cameras on a satellite, I don't think you would see much, okay? I don't think they can achieve the same level of resolution in space. So I think it's a little bit difficult to, maybe in future, I don't know, but at this stage, I find it difficult to see any immediate applications in the context of, let's say, remote sensing.
Okay, thank you, Professor.
So thank you very much for your answers. We have no time for other questions, but I see there are many questions on the YouTube channel. So maybe you can answer these questions directly from the YouTube. So thank you very much, Professor Dragotti, and it was a really pleasant conference. So goodbye.
Enjoy the continuation. Bye.